Hi, everyone. Thank you for coming through, and it's good to be here. I think I've got easily the longest journey of any attendee or speaker coming all the way from South Africa. So it's been a long journey, and it's great to see so many people here. So my name is Nick Pentreath, and I'm a principal engineer at the IBM Spark Technology Center, and an Apache Spark PMC member and committer focusing on machine learning, and also author of Machine Learning with Spark. You can find me at MLNick on Twitter and GitHub. Today I'm going to be talking about feature hashing for scalable machine learning. But before I start, we went out to a Chinese restaurant last night for dinner, and I got a really interesting fortune cookie, which I want to share with you, which I think is pretty neat. So it says, old friends will spark new adventures. And I mean, this is real, so yeah. Hopefully new friends too. So today we're going to talk a little bit about feature hashing. What is it? Move on to what is the current state of hashing with a hashing TF transformer in Spark ML, and then the new and improved feature hasher that I've done a little bit of work on, and then finally some experiments and directions for future work. So feature hashing. We all know, those of us who are machine learning practitioners, that machine learning algorithms need vectors to work on. The majority of them need numeric data. But most of the interesting data and the features that we have don't come neatly encoded in this package. So in particular, categorical features, things like tags, metadata, things like geolocation, time of day, search keywords. These are raw features that need to be encoded in some manner. Even numerical features are often not very useful in their raw format. Again, geolocation, time of day, they're often more useful if binned or otherwise transformed into something that looks more like a categorical feature. So popular methods for feature encoding are commonly known. One-hot encoding for categorical features. Take the value of that feature and represent it as a one-hot vector, a binary and vector indicating the occurrence of that feature. When all other potential values of that feature are zero. And bag of words is a kind of analogous for text or kind of token count data more generally, where we represent the document, for example, as a bag of the tokens that are present in that document with associated counts. So typically the way that this would work is, we build a dictionary mapping from the feature values to either the binary indicator or the index in that bag of words vector. So many domains have very high feature dimension that is dense, so things like images, video. But for this talk, we're really concerned with sparse domains. So these are common in areas such as online advertising, e-commerce and recommendations, social networks, video sharing, and text and natural language processing. So this is where we have very high cardinality features and categorical features or text. But in general, any one training example that we have is, has a small number of active features, so very, very sparse, but high dimensional. So in these domains, even simple models can be extremely large. So for click-through prediction in online advertising, you can be talking tens, hundreds of millions, even billions in terms of the feature cardinality and the model size. But any one training example typically has of the order of way less than 1% in terms of active features, so highly, highly sparse. In addition to that, these domains in particular often use feature engineering and feature interaction. So, the cross product of features to kind of generate more useful features, and that can explode the feature dimension significantly. And even if we use some sort of more complex models, factorization machines, for example, to help out with feature interactions and make them more tractable, we still have very large models. So we want to look at some form of dimensionality reduction here. So feature hashing is a form of dimensionality reduction, in a sense, and it uses at its core a very, very simple concept, which is called the hashing trick. I have a pointer? So do I have a pointer here? Okay. But effectively, we take the feature value and we use it, or feature name, and we use that to form the index of the feature in a feature vector. So, for example, if we're in Boston, we could take the categorical variable city is Boston. We pass that value through a hash function to get an integer or long value, and then we modulo that value to the vector size that we want. And this will be the reduced vector size to get the index of the feature. So in the case of a categorical feature, it looks very much like a one-hot encoding. In the case of a real valued feature, we might just take the feature name. Let's say we were dealing with stock price. We again do the same process. We apply a hash function, modulo that to this vector size, and we get an index in the vector. So what does this achieve? We could start out with a very high dimensional categorical domain, city, user IDs in a social network or recommendation setting, advert IDs or campaign IDs in an online advertising setting, and we can hash all of those feature values into a much lower dimensional vector. So we could go from millions, hundreds of millions, even billions, down to a few million. So the question is, does this actually work? And we'll deal with that a bit later. But the short answer is yes, it does. So why would we want to do this? Well, the key advantage is really the memory efficiency. So if we try to run a huge model with 100 million or 1 billion features, we're going to hit up against some big challenges. So, for example, in Spark, you can only broadcast a 2 gigabyte model. So that equates to about 250 million features, for example. So that is actually a hard limit at the moment. But more than that, if you try and train a model with 250 million size, in many cases, you're going to struggle to actually train that using Spark ML. So really, we'd like to bound the memory usage and be more efficient. So feature hashing does that by limiting this feature vector size. We can hash our features into a much smaller dimensional vector. We also don't need to store any mapping, so we don't need to store a dictionary of feature values to feature index. This is a big overhead. If you have hundreds of millions of features, categorical features, and you need to store that mapping in order to do one-hot encoding, or in order to do count vectorization for text, that is a big memory overhead and one of the causes of things blowing up when trying to scale these models. Another big benefit is it actually preserves sparsity. So you start off with a sparse domain. In many dimensionality reduction techniques, you end off with a dense domain. So if you're trying to apply PCA or SVD or some sort of locality-sensitive hashing, you tend to go from something that's sparse to something that's dense. And in some cases, that's okay. But we'd really like to preserve the sparsity here to get the benefits of training models on sparse feature vectors. This works well for online learning, precisely for these reasons. It preserves sparsity, it's fast, very simple, memory efficient, and there's no need to store a mapping. And then finally, feature engineering. So if we're doing in these domains feature interactions and we want to do cross products of features and these kind of things, we can actually do that on the fly as part of our hashing transformer. We don't need to necessarily even explicitly expand those features. We don't need to first create the feature interaction vector or the crossed features in it and turn our 100 million size vector into something orders of magnitude bigger. We can actually do it on the fly. This doesn't come for free, of course. There's no free lunch. And there's a fairly big downside to feature hashing, and that is that you lose this inverse mapping. Now, because you don't have to store it, you gain memory efficiency and speed, but you can't go from the hashed representation back to the original representation. So this is a problem for interpretability and things like looking at feature importances in your models and so on. So it is something to consider when looking at using this. But again, if you're doing certain dimensionality reduction techniques, like I mentioned before, PCA, SVD, and so on, then you have a similar issue. So it's not common, it's not unique to feature hashing. And then the second major one is, obviously, if we're hashing values into a lower dimension, we could end up with hash collisions. So that's when two features are going to be hashed into the same index in our feature vector. So clearly that is going to mangle a bit our results. But as it turns out, the impact of this is actually not so great. And it can be alleviated a little bit by using signed hash functions. So the idea here is that you would use either the two hash functions, one for the sign of the feature value and one for the index, or there's other ways to use one hash function. But if on aggregate two or more features are actually being hashed to the same location, and one of them is positive, one of them is negative, then you have a kind of zero expected value. So in aggregate, this will tend to it'll cancel each other out, and you won't get too much impact. Okay, so feature hashing has been made popular by libraries such as FilePowerWabbit and scikit-learn, and it actually already exists in Spark in one form. So this is hashing TF, hashing term frequency. And this transformer takes raw sentences and turns them into this bag of words representation, term frequency. It uses exactly this hashing trick to compute the feature indices. So it'll hash each term, get a hash value, and it'll modular that to your vector size, and that is the index. And the value will be either the term frequency or token count, so the number of times that term appears in the document, or optionally you can just make it a binary occurrence. A typical usage is something like this. You would first start off with your text. You would have a tokenizer, split that up into tokens. Here I've called it terms in this data frame. And then finally, you pass it through the hashing TF. So you can see here pretty much how this works. You end up with a vector size. In this case, the default is 2 to the power of 18. So it's 260,000. And you can see that each term has actually been hashed into what looks like a fairly kind of random place in that vector. But now, the challenge that I've personally faced and that you'll face if you're trying to use hashing TF to deal with categorical features is that it obviously takes a sequence of terms, and most of your data is not going to be in that format. You might have city equals Boston, New York, etc. So I've personally done this, and I kind of like to call it stringify. And you can basically take what you have at the top right there, which is a data frame of categorical columns, and you operate on the entire row at a time, and you kind of mangle it together and form a sequence. And each element in that sequence represents the categorical feature. So it's kind of a one-hot type encoding. So you start off with I1, I2. These are just some example features, and you end off with a sequence that says I1 equals 1, which is the kind of indicator for that particular categorical feature. I2 equals 2, I3 equals 5, and so on and so on. So once you've got it in this format, it actually ends up working very much like feature hashing for categorical features. And you can use it like that. But the problem here is that unless you wrap this up in a custom transformer, it doesn't fit neatly into a pipeline. So I've used this before, but then you end up either having to use data frame operations or write a UDF, or often, as you see here, dropping down to use RDDs, and that breaks your pipeline. You can't just slot this into your Spark ML pipeline. So that led to thinking about, could we do something more native, and could we create a more flexible and powerful feature hasher in Spark ML? So the goal is to do flexible, scalable feature encoding using this hashing trick, but to support multiple input columns of various types, so both categorical features and real features, and to do one-shot feature encoding. So this is a lot more scalable. We don't have to put together multiple string indexes and one-hot encoders, we can just pass a bunch of columns to this feature hasher and get out our vector at the end. The core logic is extremely simple and pretty much exactly the same as hashing TF. So this is how it works. It operates on an entire row at a time. So it's actually, the core will just be a user-defined function that takes a row. Or actually is a sort of struct object taking the values of all the columns that we pass in. And all we do is we decide whether it's a categorical or real feature. So for this simple version, I can't just assume that, okay, if it's a string, it's going to be a categorical feature. If it's numeric, it's going to be real. So dealing with categorical features, we represent it as a string where the field is, field name or feature name equals feature value. So city equals Boston, as we saw before. We simply hash that to get our hash value, and the value, hash value that'll form our feature index, and the value is just 1. So it's a kind of binary representation. So for strings, it ends up being something that's effectively a one-hot encoding. So for numeric values, we take the feature name, the field name, and we hash that to get the index, and the value is obviously going to be the value. So this is what it looks like. If we have a couple of categorical features and a couple of numerical features, we can see there that country equals US gets hashed to the same location consistently. So in this case, I think it's feature index 104.522. And you can see that categorical features have been encoded as binary, kind of one-hot encoding style, and numerical features have been encoded as their actual values. So effectively what we end up with at the end is the same as if we had done string indexing, multiple string indexes and one-hot encoding for categorical features, and we had done kind of vector assembler and put them all together. But the difference is it happens in one pass, and it's obviously using the hashing under the hood to do this dimensionality reduction. So right at the beginning, I mentioned that this seems really simple. In fact, it seems trivial. I mean, you just apply a hash function. You hash the features into a smaller vector. You're going to have these hash collisions. So surely it doesn't work. Surely you're just going to get garbage. But because we were dealing with highly sparse features, it turns out that the small amount of hash collisions there might be tend not to hurt our performance much. Because in general, as long as we've got a good hash function that spreads out the hash values, we end up with where there is a collision, because we've got a machine learning model that's kind of learning approximately anyway. Those collisions don't tend to occur often enough to really hurt us. So I'll show you a couple of results from some experiments just to actually illustrate this. This is a very small data set just to show the text use case. And this is actually using hashing TF. So it's a Kaggle email spam data set. As I said, very small, only a couple of thousand rows. I applied basic tokenizer, and then the same pipeline we saw earlier, basic tokenizer, followed by hashing TF, followed by, in this case, logistic regression. And what you can see here is that the count vectorizer is kind of the baseline. That is the full vocabulary. I think it's about 50,000 terms. And we see here the AUC performance of the hashing TF. So it's pretty close. There's not much difference. And in fact, at smaller hash bits, we see that it's got better performance, which is interesting, right? So we'll think about that a little bit. But this is without regularization. So when I saw this, I thought, hey, that's a bit strange. I would generally expect that smaller hash bits has worse performance. But if we add regularization, we actually end up with something a bit different. So the count vectorizer is better overall. Again, hashing does similarly, but slightly worse. And what you can see is that at lower hash bits, we got very similar performance with and without regularization. But at higher bits, it tends to be kind of converged to what we would have in the count vectorizer. So it actually indicates to me that hashing in this particular domain, in sparse feature domains and in text, can almost play a little bit of a regularization role, because when you get collisions, they are kind of canceling each other out in a way. So unless it's a very, very informative feature, and for email spam, only a few features are going to be very informative, this kind of almost acts as a bit of sparse regularization, which is quite interesting. So what's more interesting, perhaps, is to look at larger scale data sets. So a classic example of large sparse data is ad click prediction, online advertising. Unfortunately, we've got a couple of nice data sets to look at, so again, from Kaggle. The first is the Criteo display advertising challenge. Second is Outbrain, which is a recent click prediction problem. And then finally, probably the largest click prediction, publicly available click prediction data set, which is the Criteo terabyte log data. So in the first one, we can see we've got 45 million examples, about 34 million categorical features, extremely, extremely sparse. And the number of non-zeros per example is of the order of 39. For Outbrain, similar kind of sparsity, 80 million examples, 50 million features in the particular feature extraction that I used, which is very simple. And again, they're something of the order of 8 non-zeros per training example. And Criteo terabyte log data is a larger superset of the Criteo display advertising data. So it's got similar kind of sparsity pattern, but a lot bigger. I mean, I used the first 7 days. That's 1.5 billion examples and 300 million features. The full data set has many billion, I think sort of 7 billion examples or something, and about 800 million features. So to look at a couple of illustrative characteristics of this data, this is Criteo. We've got the unique feature values per feature on the left. So you can see that in these domains, typically you have a few features which have extremely high cardinality, and these are typically going to be things like the user IDs in your system, the advert IDs, the geolocation. It could be search keywords in display advertising for search. So a couple of features are going to effectively dominate the size of your feature vector. And on the right, we see feature occurrence. So we can kind of see that it tails off extremely quickly. And you have a few features that occur often, and many of them hardly occur at all. So again, this is kind of where the power of feature hashing as dimensionality reduction comes from, because many of these features are not occurring very often. If you're hashing them into a smaller vector and you get a few collisions, it's generally not going to, it may not hurt performance all of that much, because in any case, even if you're learning on the full scale problem, you wouldn't actually be able to learn much from the occurrence of that feature a few times. So challenges that I ran into when trying to even run kind of baseline benchmarks is that if you try on some of these largest dimension data sets to just do what your first thought would be, okay, I'll one-hot encode all the categorical features. So I'll use my string indexer and one-hot encoder, and first of all, it's a bit of a nightmare, because you've got a pipeline with 80 different stages, because you can only operate on one column at a time. But secondly, I've consistently not been able to ever actually get it to run. I hit out of memory errors, dropped executors, all kinds of strange things. Very difficult to kind of diagnose exactly what's going on here, because one-hot encoding should work, right? It's really simple. It should just kind of work out the box. But for these very high cardinality features, it blows up. I think it's got something to do with both the size of the dictionary mapping and also the attributes the metadata attributes that are getting attached to the data frame columns that come from one-hot encoding. So still some work to do there to actually figure out why this is happening. So the results here, you can just see the AUC performance for a couple of different hash bits. Near 24 hash bits for both of these data sets. In particular for Outbrain, you're actually getting close to what the baseline is. And kind of no dimensionality reduction. And to the left at 18, you're actually getting significant reduction. You're taking a raw feature dimension of 30 or 50 million down to 200,000. And you can pretty much see that there's a bit of noise around the AUC, but it's there's almost no difference, right? I mean, you're getting a huge benefit in terms of speed and in terms of efficiency for virtually no cost in terms of accuracy. And I mean, I won't go I didn't actually get a lot of time to run larger scale experiments on the 1 terabyte data set. But you can successfully train this model. It's 300 million original features, which is basically impossible on Spark to run just due to the out of memory and the issues with the 1 hot encoding and the 2 gigabyte broadcast limit. You can hash this down to 16 million due to the 24, run it successfully. And as we saw before, your accuracy is essentially unhurt. So in summary, feature hashing is a fast, efficient, flexible tool to encode both categorical and numerical features. It can scale to extremely high dimensions in sparse data without giving up pretty much any accuracy. And this sort of basic implementation that I've worked on supports multiple column one-shot encoding, so one pass multi-columns, and avoids these common issues that you'll have with scaling, string indexing, and one-hot encoding. Some future directions, working on actually just including this in Spark, whether it's as a new feature transformer or an extension to the existing hashing transformers that are in there. So there's the Jira ticket. Please watch it, follow it, and any comments welcome. And I think there's a lot of improvements that can be made. This is a very basic version. We could look at adding the signed hash functions to allow the kind of zero expected value benefit there. Projects like Valpower allow you to do this on the fly, feature crossing, feature interactions, and namespace crossing during at transformation time during encoding. I think that would be really interesting. And finally, for those of you who know scikit-learn, they have a dict vectorizer, dictionary vectorizer, which is effectively working very much the same as the feature hasher, except you actually do an exact mapping, and you can create, store the inverse mapping and get a kind of exact version of it. But again, the idea there would be to allow one pass encoding of multiple columns, both categorical and numerical, at the same time. Yeah, so there's a few references. They'll be up later when they post the video and the slides. And thanks very much for listening. Any questions?
Sorry, stop behind you.
Is there a representation for the random guesser in hashing? And another question, what is the 1 bit do? I guess I'm wondering if you could sort of think about what the hashing is doing by whether it's driving you to random guessing or away from it.
Sorry, I'm not sure I fully understand the question. You're saying,
so
how does it relate to random guessing?
Some models are able to imitate other models, right? So you can, is there a point in the hashing space that imitates a random guesser that would have an AUC of 1/2?
Oh, right.
And have you tried the 1 bit encoder?
I haven't tried that.
Okay.
It's a good question. As you compress down, depending on the feature size, I didn't go too low because eventually the collisions will eventually cause problems. So eventually, if you hash down to a very, very small space, everything is going to collide, and your AUC should, in theory, then pretty much go to 0.5. True. So I think it'll be interesting to try. I haven't tried it. I think if you had the signed version where they were sort of canceling each other out, you probably would get to a point where you weren't learning anything, so it was the same as random guessing. Yeah.
Hi. With respect to collision resolution, is the feature hasher API such that you could implement your own collision resolutions, like maybe a mean of a separate chain or something like that, as opposed to like a linear probe, which
good question. At the moment, it really is very, very simple. So the idea is to start with something simple, do a few experiments, kind of verify, and then work from there. But I think there's some interesting ideas, as you said, multiple probing, or in some cases you can use multiple hash functions to try and get kind of better collision, these kind of things. But so the API itself, the current version doesn't support that, but I think that would be a good addition.
So two small questions. That was great. First question: are there models that are more sensitive to the hashing trick than others? Because I guess that some do the splitting of features and might be more sensitive to these random numbers that are generated by the hashes. And second question: what do you think of in the scenario of the string indexer, one-hot encoding, doing kind of a top K string indexer that just keeps the most popular nominals and then just does the one-hot encoding on that reduced set? Is that a good alternative in your experience, or is the hashing trick the way to go in almost all cases?
Yeah, I mean, some good questions. I think in terms of sensitivity, it depends on the domain. I've kind of pick domains, sparse feature domains, high dimensions, where hashing, I know from papers and from experiments that it works well. But it certainly doesn't work well in all domains. So it's a tool. It's a tool in the toolbox, and if you know that you're dealing with the domain where it does work, then it's definitely worth trying. I haven't, it shouldn't, or probably won't work so well in dense domains. In my experience, I haven't come across an area in the kind of binary classification with fairly sparse kind of features where it doesn't work fairly well. And in terms of the, just remind me of the second part of the question. Top K, yes, sorry. Yeah. So that's also a very good question, and it's something that I didn't have time to kind of do much experimentation on here. But one of the ways that you can try and limit the problem is exactly to do top K or kind of most popular terms or categories. So with this sort of stringify hack that I've used before, the count vectorizer, you can either use the hashing TF. So once you've transformed into this feature name equals feature value sequence of strings, you can either use hashing TF or you can use the count vectorizer, which is an exact form of that. And there you can select the vocabulary size, and it'll do exactly what you say, do a top K up to the vocab size. And I didn't have time to run that many experiments, but particularly in domains such as text, where we know that the tail end is not going to make much difference, that you should get similar performance to if you use hashing. So yeah, that is definitely an option, both for one-hot, the string indexing one-hot encoding pipeline, as well as the kind of count vectorizer version for text.
Yeah, nice talk. I really like the analogy between the bits and regularization, so it was really nice. One question I have is that have you tried something like locality sensitive hashing, where you try to make the hashings a little bit smarter in that if the original features that are similar are going to be mapped down into some hashing that are similar to?
Yeah, I mean, I haven't tried LSH for this purpose, so it's an interesting idea. I mean, I've used LSH quite a lot when it, for the sort of nearest neighbor search in recommendations, for example. I've used it a lot there, but not for kind of hashing, feature hashing. So interesting idea. I think it could work to the one area where the reason hashing works pretty well, and it's dependent on the hash function, is because it should spread out the features evenly. So in some sense, you may not want some of the features to get hashed into some of the buckets because you might actually increase collisions there. So it could be interesting, but I haven't really done it, no.
Thanks, everybody. Please join me in thanking our speakers.
Thank you.
Lunch is served.